significant figures. And so why use significant figures? And the idea is that all measurements have some degree of uncertainty, meaning there's some, estimation involved in it. For example, let's look at the signs entering different cities. So how certain are these towns of their population? So let's look at some different examples here. So we got San Jose, and it just says population 920,000. Okay, probably pretty accurate. Let's look at another one. Holmen, Wisconsin, population 7,336. All right, I think I'm going to guess that's pretty darn close, right? Let's look at some other ones. We got the town of Broke, population of 400 people. All right, I mean, it's got to be relatively accurate. I mean, not too many people. Although, saying 400 is a little suspect. Schubert, 237. And this is my kind of town because they got biscuits and gravy on Sundays. So Schubert, 237 people in Nebraska. Then we got Toronto, 2,482,000 people. Now, as we're kind of looking at this, the big question is, do you think that in Toronto there is exactly 2,482,000, or do you think it's just kind of close to that? And that's kind of the big thing with significant figures. And so why use different significant figures? So when we report numbers in chemistry, the number of significant figures indicates how certain we are of that particular number. So it indicates the increments on our measurement device. That's kind of the big thing. And so let's talk about some of our rules for significant figures. So our first rule, as we kind of are looking at it, says that all non-zero numbers are always significant. So non-zero numbers are always significant. And so let's look at that in terms of some examples here. So our first example, we have 555. And so that means that each of these fives is considered a significant figure. So this number has 3 sig figs. All right, let's look at another one, 7.2. So same idea, 2 non-zero numbers. And since they're non-zero, that means that they're both significant, meaning 7.2 has 2 significant figures. All right, so that's our first rule. Now our next rule, as we're looking at it, says that leading zeros that come before non-zero digits are never significant. Now when it says leading zeros, it's talking about zeros in front of a number. So generally you see this with like decimals. So it'd start with like 0 point, something. So those zeros up front are considered not significant. And so one example would be 0.02. So all of the leading zeros, meaning the zeros in front of the 2, are not significant, meaning that in terms of our sig figs, we only have 1 sig fig in this number. All right, well, let's look at another example. This time, 0.0255. Okay, well, the same thing. Our leading zeros aren't significant, meaning that the 2, the 5, and the 5 here are considered significant. So that means that we have 3 sig figs in this number. All right, let's look at another example here. And so we got rule number 3. And it says captive zeros between non-zero digits are always significant, meaning it's kind of like a, sandwich where zeros are in the middle of other numbers. And so let's kind of look at this. So one example would be 707. So as we're looking at this, because the zero is trapped between 2 other numbers, that means that the 0 is significant. So it's 3 significant figures for 707. Now let's look at another one. And this time we have 4001. And so here we have 2 zeros that are trapped between a 4 and a 1, which means that all 4 of these numbers are considered significant. So this has 4 sig figs. All right. Now, with this, let's kind of go on to rule number 4. And this is where things get a little bit trickier. And so rule number 4 says trailing zeros at the end of a number are only significant if there's a decimal point. And so with this, trailing zeros are the zeros that go after a non-zero number. So like if you think about 1,000, 1,000 has a couple zeros after the 1. Those are considered the trailing zeros. So now let's look at some examples here. And so our first example is 100. Now remember, they're only significant if there's a decimal point. So here, there's no decimal point, which means that the only significant figure here is the 1. All right, let's look at another example. And this one is 100 with a decimal point. And so 100 with a decimal point means that those zeros are significant, which means that this is 3 significant figures. Now, I know we only have 2 examples here, but let's talk about a couple other examples, just as we're kind of looking at it. So let's just say, we'll stick with the 100 theme. Let's say it was 100.0. So even after the decimal point, that decimal point there does mean that this 0 is significant. And so that would mean that this would be a number that has 4 significant figures. And then let's just kind of make it really extreme here. Let's just say it's like 100.0000. Because of that decimal point, all of those zeros are considered significant, which means that this has 7 sig figs. So I know this is kind of a little confusing here, but the idea is the decimal point shows us our degree of accuracy. So just like with measurement, when we talked about measurements, sometimes a measurement falls right on the line, but you still have to write like 0.0, right? So the same idea is true with significant figures. It's showing us in terms of our measurement how accurate we were able to measure. And so that's kind of the big idea with significant figures, is it's showing us, because in chemistry, everything is based off of measurements, in chemistry, exactly how accurate that measurement was. So that's the overall purpose of significant figures. Now with this, we have one more rule, and I missed this one. So 100.0, we already talked about it, 4 sig figs. And so let's look at our last example here, rule number 5. And so for rule number 5, this one says that exact numbers that come from counting and definitions have an unlimited number of sig figs. Now, the reason we say that they have an unlimited number of sig figs is because something we'll kind of talk about later on is how sig figs actually play a role in rounding when we do calculations. And so basically this rule is kind of more tied into that. But let's kind of look at some examples here. And so our first example is, let's just say you had 3 books. Well, we say that this is an infinite number of sig figs because you counted the 3 books. Meaning the idea is it's not just 3 books, but let's go back to that idea of trailing zeros. It's 3.00000000 to infinity books. There's no more, there's no less. It's exactly 3. And that's why it comes down to this idea of being an infinite number of sig figs. And so that's one of our examples that comes from counting. Let's look at another one that says that there are exactly 12 inches in 1 foot. Again, this is something that we say has an infinite number of sig figs because there's exactly 12 inches in 1 foot, meaning there's 12.00000000 to infinity inches and 1.0000 to infinity foot or feet. So that's the idea with this last rule, or rule number 5. So now that we've kind of talked about this, let's kind of look at some more examples here. And so our first one, we got 950. And so for this, Because there's no decimal, the 9 and the 5 are significant, but the 0 is not. So that makes this 2 sig figs. So let's look at our next example. So B says 0.45. Now remember, the leading zeros aren't significant. So we just look at the 4 and the 5. Those are both significant, so we say that this is 2 sig figs. Okay, now we have 0.450. Now again, because of that decimal point there, that decimal point does mean that this ending 0 is significant. So that means that this is 3 significant figures. Now we have 890 with a decimal point. So because of the decimal point, that means that the 0 after the 8 and the 9 does count. It is significant. Now we have 803. So even though the 0 is sandwiched, all 3 of those count, making this 3 sig figs. 3.43. This one's easy. 3 sig figs again. Then if we're looking at our next one, 0.0000004, remember all those leading zeros don't count because there's no non-zero digit up front. And so that means that this is 1 sig fig. So just kind of on a side note, if it helps clarify things, because this is a 0 or it's starting with a 0, all of those zeros don't count. But just in case you were curious, if it was like 1.0000004, this would then be a grand total of 8 sig figs. So 1, 2, 3, 4, 5, 6, 7, 8. So just in case you were kind of curious why it was only 1 as opposed to it being like 7 or 8, for example. And then finally, letter H, we have 0.007500. Now remember, leading zeros don't count. So that means that the 7 and the 5 automatically count. And then because of that decimal point, that means that these other 2 zeros also count. So that means that this is a grand total of 4 sig figs. All right. So now that we've talked about sig figs, let's kind of talk a little bit about one more idea, and that's the idea of rounding 2 significant figures. Now, a lot of times we have to round to a certain number of significant figures at the end of a calculation. And so the idea is first you need to determine how many sig figs are in the original number, then round that number to the correct number of sig figs. So our question here is, how do you write the following numbers with 2 sig figs? Well, if we start off with 56.7, this originally has 3 sig figs. So if we need to write it with 2 sig figs, that means we need to round based on the first 2 significant figures. So the 5 is going to stay, the 6 counts for the second sig fig, and so now what we need to do is there's kind of our cutoff line, and we ask ourselves, does a 7 round up or does it round down? Hopefully you agree and say that it rounds up. So that would mean that this would be 57 when it's rounded to 2 sig figs. All right, well, let's look at another one. We got 157. Again, this one has 3 significant figures originally. So we do the same thing. We keep the 1, we keep the 5, and then we look. Does 7 round up? Of course it does. So the 7 causes the 5 to round up to a 6, making this 160. And remember, this only has 2 sig figs because there's no decimal point here. So as long as we don't add the decimal point, it's only 2 sig figs. All right, our next one, 1,458. Whoa, this one has 4 sig figs. So we do the same thing. We look at the first 2 digits that are significant, so the 1 and the 4. So there's our cutoff line. And then we ask, does the 5 cause the 4 to round up? Now, whenever this kind of happens, you only look at the first digit afterwards. So in this case, we're looking at the 5, and we're looking to see if the 5 causes it to round up. And in this case, of course it does. So that means that this number becomes 1,500. Now, this does bring up kind of an important point here. Let's say instead of 1,458, let's say it was 1,448. and we needed to round to 2 sig figs. Now, if we keep the 1 and the 4, and then we look at the next number, so for this, we only look at the 4. We don't care what's after that. So even though this is an 8, in fact, it could be a 9, it could be several 9s. It really doesn't matter. We're only going to look at the very next number. And so that is one important point when it comes to rounding, is you don't want to look at this 9 and say, oh, well, the 9 causes the 4 to round up, which then would cause this to round up. No, it doesn't work like that. You only look at the very next number that's getting cut off. All right. Hopefully there aren't any questions about that. So let's look at another one, 58.24. And so for this is 4 sig figs originally. And so now, as we go through it, we keep the 5 and the 8, and then we look, does the 2 round up? Nope, it doesn't. So this number just sticks at 58. And then finally, our last example here, we got 59.8. And so with 59.8, this is 3 sig figs. And so as we work on rounding to 2, we keep the 5, we keep the 9, the 8 gets left off. And so the 8 is going to cause the 9 to round up. Now in this case, that means our number here is 60. But 60 by itself is just 1 sig fig. So what can we do to make it 2? Because we can't leave it at 59, and we can't round it up to 61 because that's changing it too much. So it has to be 60. So the one thing that we can do to make it 2 significant figures is to add that decimal point, making it 60 point. All right, let's look at a little bit more, or a few more examples here. But this time we're rounding to 3 significant figures. And so our first number, 167.2, this is 4 sig figs. We look at where we round. So the 1, the 6, the 7 stay, and the 2 does not cause the 7 to round up, so it's just 167. All right, then our next one, 1,111. Again, 4 sig figs. We keep the first 3, and then the last, there's our cutoff. We look, the 1 doesn't cause it to round up, which means that it's just 1,110. Now that's an important point. Yes, we're cutting off the last 1, but remember it turns into a 0. So that's a very, very important point, is if you're cutting stuff off when you're rounding, remember it turns into zeros. It doesn't just disappear. There's a big difference between 1,110 versus just 111. So make sure you keep that 0. Otherwise, our next example, we got 1,458. We keep the 1, we keep the 4, we keep the 5, and the 8 causes the 5 to round up. So this is 4 sig figs. So it becomes 1,460. And then finally, this one is a little tricky. We got 1. It only has 1 sig fig, but all right, so our last example here, we have 1, which is really only 1 significant figure, and we need to write it with 3. So the way that we turn fewer sig figs into more sig figs is by getting a little, kind of creative with the use of a decimal point and zeros. So if we need to write 1 with 3 significant figures, it becomes 1.00, which now has the 3 significant figures. All right, so now this brings up another kind of big question here. Well, how do we write the number 1,000 with 3 sig figs? Because keep in mind, if it's originally 1,000, this is only 1 sig fig, right? Now, if we add a decimal point to the end, all of a sudden, this is 4 sig figs. So we can't just add a decimal point to the end. But if we add it after the first 3 numbers, we just turned 1,000 into 100. So we can't do that either. So all 3 of these options are bad. And so the way that we can do it is actually through using scientific notation. And so anytime you need to kind of change a number with a lot of zeros, and get it so it only has a certain number of sig figs, scientific notation is the way to go. So with that in mind, when we're asked how do we write the number 1,000 with 3 significant figures, just like we did in our last example, we can write 1.00, and now that has 3 significant figures, but in scientific notation, it's going to be times 10 to the positive third power. Now, using scientific notation, basically the idea is anything before the times 10 part is your sig figs. So if you're trying to round to a certain number of sig figs at any point, whatever comes before the times 10, whether it's a positive exponent or a negative exponent, that part is your significant figures.